Hello everyone. We now know how to calculate the rotational inertia of a bunch of point masses. And it's the sum from I equals 1 to n, where n is the number of point masses, of all of the mr squareds. But what if your object is not a point mass, or several point masses? Right? Then how can we figure out its rotational inertia? Right? As most things in the world, we cannot approximate as point masses. Well, this is where things are going to get a little more complex, right? So let's look at a general situation. Let's say we have this kind of egg-shaped disky kind of thing here, okay? It's got a total mass we're going to call capital M. Capital M means big mass, right? Total mass. Its rotational inertia, its axis of rotation is right through the center. Why not? So this thing can kind of spin around this point, okay? So how are we going to figure out the rotational inertia of this thing? Well, one way we could do it is to break it up into a bunch of point masses. Right, so we could take a point mass out here, which has a mass which I'm going to call little m. Right, so little m is just the point mass, big M is the whole object. This little m is a perpendicular distance r away from the axis of rotation. Same r we've been using, right? How far the mass is away from the axis. And of course we know that this point mass, right, has a rotational inertia of mr squared, little m, little r squared. But if we broke it up into n pieces, right, then the rotational inertia would be the sum from I equals 1 to n of all of the mi/ri squareds. But this would just be an approximate rotational inertia. Right? It wouldn't be perfect. We probably couldn't break it up into perfect little pieces. Right? So there might be some around the edges that might, have little issues and those kinds of things. So how could we make this a better approximation? Well, what could we do to these little mass increments? Yes, as we've done before, we could shrink them in size, or in other words, increase the number of pieces. Right? As each piece gets smaller, as the number of pieces inside this get bigger, we'll come closer to actually breaking it up into, the same size distinct pieces. Well, in math, doing something like that is taking the limit. So we could take the limit as the number of pieces approaches infinity of the sum of all of, from I equals 1 to n, of all of the mi/ri squareds. We are taking the limit of a summation. And when we've done that in the past, we know that that is kind of the definition of an integral. So we could take, to find the rotational inertia of a continuous object, we could take the integral of r squared with respect to mass, r squared dm. Right, so the dm then means that these are so tiny now, they're infinitesimal little mass increments. Right, and we're going to sum them up over the entire body. Right, so we know how to do some integrals, so that's going to allow us to find some rotational inertias of continuous objects. And in fact, there's a handful of these, 7 or 8 or something, that you need to know. You need to know the rotational inertias, and you need to be able to prove or derive the rotational inertias from basic principles. If that takes calculus, you're going to need to be able to use calculus. In some cases, we can get away with geometry type arguments, in which case you're going to have to be able to repeat these. Often this shows up on an AP test on a free response question as like a part A. Show that the rotational inertia of this object is this around this axis. And then you have to be able, or even they'll use the word derive if they want to be full on powerful, and then you have to be able to do that. It might be worth 2 or 3 points out of the total 15 points. So note there that if you can't do it, they've told you what rotational inertia is going to be in the end, so you can do the rest of the problem then, for which you would need that rotational inertia. Right? So you can still do the rest of the problem, you just can't prove it. Right? So that's what we're going to spend the next day or two here working on. And along the way, there's even a lab to help us figure out some of these, as you're going to see. So, first one we're going to do, so this is kind of a big example, going to take us a couple of days. Determine the rotational inertias, otherwise known as moment of inertia, remember, for the following objects. So A is the simplest kind, a hoop of mass capital M and radius r about an axis through its center. Can you see how this is three-dimensional, I hope? See the axis right through the center, right? And the radius of this hoop is r. Okay. according to what we just determined, right, the rotational inertia of this hoop would be the integral of r squared dm. Okay? In other words, we're going to break up this hoop into tons of little infinitesimal increments dm, right, and then integrate over all of those. Well, note here something, though, about all of those little mass increments. How far away is a mass increment right here from the axis of rotation? R. How about one over here? R. How about one over here? R. Yeah, a hoop, which by definition is basically a circle, right? All of the mass increments are the same distance away from the axis of rotation. So for r dm, little r is capital R is a constant. So if we plug in capital R, don't lose the squared, you can pull it outside of the integral because it's a constant. Well, what's the integral of dm? If we sum up all the teeny little mass increments, what are we going to get? We're going to get the total mass. So the rotational inertia of a hoop is mr squared about its central axis. Now be careful, if it's any other axis, okay, then it wouldn't be mr squared, it'd be something else. But we'll get to that, right, as we go. Now hopefully you recognize this as kind of a maximum, right, because all of the masses are all as far away from the center as they can get, from the axis as they can get, right? There isn't some mass inside of this. So note that it's mr squared here. So a lot of our other objects are going to be some fraction of this, right? Because they're going to have mass that is closer than the outer rim, right? And if mass is closer, it has less rotational inertia. Okay, so let's look at kind of a three-dimensional hoop, which would be what we call a cylindrical shell. All right, good way to think about this is kind of like a can which has the ends cut off, right? So this is empty and this is empty down here. So I've made it clear so that we can see through it, okay? So this is a thin cylindrical shell with mass, total mass capital M and radius capital R, about an axis, again, through its center. Can you see that? Right? Then you might think, like, how could you even do that? Right? How could you put an axis through its center when there's a hole, when there's nothing in the middle of it, right? Well, this is going to be very useful when we talk about objects that roll. Because if we roll this object, doesn't it rotate about its center? Okay. Well, how are we going to do this? We could do this with calculus, but we've already kind of done the calc. So what we're going to do instead is we're going to break up this cylindrical shell, which has a mass m and a radius r, into a series of hoops. Each hoop will have a mass increment mi, and each hoop also has a radius r because the whole cylindrical shell does. And then we're going to sum up the rotational inertia of all of these little hoops, right, from the bottom to the top. With me? So we're going to slice this, if you will, into hoops, and then we're going to add all those hoops together to make the shell. Well, as we just found in part A, we know the rotational inertia of a single hoop, right, would be the sum of all of its mi-r squareds. Right? Each hoop would have a rotational inertia of mi-r squared, and then we're going to sum all those. But what's true about r for each hoop? Well, it's the same. It's a cylindrical shell. Right? So r squared is a constant, which can be pulled outside of the summation. And what's the sum of all of the mi's if we add up all the masses of all the little hoops? It's capital M. So a cylindrical shell about a central axis has the same rotational inertia as a hoop about the central axis of the same mass and radius. You gotta be a little careful there. That's a little weird, right? So if your hoop has the same mass and the same radius as this entire cylindrical shell, it'll have the same rotational inertia. Okay? Because again, all of the masses are the same perpendicular distances away from the axis of rotation. And that's really what this r is the distance perpendicular to the axis. We don't take an r from some point down here and draw it at an angle up to there to pick up a little increment at the edge, at the lip. Right? We go from the axis of rotation perpendicular to it to find r. So hopefully this makes sense, that a hoop and a cylindrical shell kind of work the same from a rotational inertia standpoint because of where all of their mass is located. Right? The same distance away from the axis of rotation. So here's one that's a little harder. A thin rod of mass m and length l about an axis perpendicular to the rod and through its center of mass. Now, of course, where's the center of mass of a thin rod? We actually proved that. That is the one center of mass you have to be able to reproduce on a test. And when we did that, we found that it was exactly in the middle. Of course, symmetry arguments kind of make the same thing, but you might have to do, right, the 1 over total mass integral of all of the RDMs kind of thing. Or MDRs, sorry. No, RDMs. Right, to do the center of mass. So this is around the axis, if you can imagine this spinning around it, right? This is similar to the rod we used in the last few labs we used. Although that rod really wasn't a thin rod, right? Because it had a hole in the middle of it. But it's a decent approximation, okay? So this is essentially a one-dimensional rod. That's what thin means in math, okay? It means it's essentially one-dimensional. Okay. So if the rod has a mass m and a length l, total length l, how far away from the axis of rotation is this end? Well, if we put our coordinate system through the axis to make the axis 0, right, the coordinate of this end would be, if this end would be positive l over 2, and the coordinate of this end would be negative l over 2, right, half of l. Everybody okay with that? It's going to be useful in our integral in a moment. So we're going to take the integral of all of the r squared dm's, which means we're going to take this rod, and we're going to, first of all, let's define that we mean a thin rod, and therefore we can change the r to an x because it's one-dimensional. Right? Just one-dimensional. We will look at some two-dimensional ones eventually here. Some special three-dimensional ones like we just looked at. Right? So we're going to make this the integral then of x squared dm. Now, if we pick up our little mass increment somewhere along the way, that little mass increment will have a mass we will call dm, right? Infinitesimal now if we're going to do an integral, right? And then it will have a width we will call dx. So it's a distance x away, all right, from the axis here, but it's got a width dx. With me? Now we run into a problem. And our problem is that as we choose little mass increments up and down the row here, the mass of those little increments isn't going to change. The position of those mass increments are going to change. But our integral is with respect to mass. So we have a problem because we have a function where x is going to be the variable, but we're integrating with respect to a different variable, the mass. We can't do that. So we're going to have to do something called a change of variable. And to do that, we're going to use a quantity that might seem a little familiar because we used it back in the center of mass proof. It's called the linear density, one-dimensional density, denoted in an equation by a lowercase lambda. Again, hopefully you remember this from center of mass. The linear density of this uniform density rod is total mass over total length, right? Because it's constant the whole way through, so we just take the total mass divided by total length. Note, three-dimensional density is mass per unit volume. One-dimensional density, linear density, is mass per unit length. This is a quantity which actually gets used. It's sometimes the way different wires might be listed. So you might buy a wire based on its linear density. How much mass does it have per centimeter or per inch or something like that? Okay, get that idea? Now, the linear density of the entire rod is m over L. But what's the linear density of our little mass increment? Well, wouldn't it be dm over dx, where dm is the amount of mass in that increment and dx is the width of that little increment? Right? Solve. dm is lambda times dx. Substitute, and we have changed the variable. See how I put lambda dx in for dm? Now we have an integral where our variable is x, and we are integrating with respect to x. And notice I've been able to add limits of integration, because x changes, our little mass increment locations, change from all the way on this end, negative L over 2 away from the axis of rotation, to a little mass increment at this end, which would be L over 2 away from our axis of rotation. So there's our limits of integration. Very important to pick those up. Note, although we're not going to do this for a while, but if we wanted to look at a different axis than through the center of the mass, none of the work we've done right now would change. All that would change would be the limits of integration, right? If we move, let's say we move this over here, now this would be different, wouldn't be half of the way, and this would be more than half of the way. With me? So then it would just change the integral, not the process. Now, lambda is constant because it's a uniform density rod, and therefore we can pull this outside of the integral. And now we have a fairly simple integral. What's the integral of x squared with respect to x? Well, add 1 to the exponent, divide by the new exponent. All right, that would make 1/3 x cubed. And we evaluate that from our lower limit, negative L over 2, to positive L over 2. Now to make life a little easier, I'm going to factor out the 1/3 and put it over here with the lambda so that we just have x cubed left inside, okay? And there we go. So we've got lambda over 3, and then we plug in positive L over 2 cubed minus negative L over 2 cubed. Now you got to be a little careful with the negative signs, right? L over 2 cubed is, of course, L cubed over 8, but negative L over 2 cubed is negative L cubed over 8. And minus a negative will be a positive. Very important that we get the right thing here, right? Cubed means negative times a negative times a negative, right? So you get a negative out. So that becomes L cubed over 8 plus L cubed over 8. Add those together, you get L cubed over 4. Multiply it out, and we get lambda L cubed over 12. But this is not in terms of our basic variables, m and L. Right? This is in terms of L and the linear density. But we can substitute in for the linear density because we know that the linear density, because this is uniform, is m over L. So plug that in for lambda. And we get 1/12 m over L times L cubed. So this L cancels out with one of the L cubes, and we get 1/12 ml squared. A thin rod about an axis through its center perpendicular to the length. Notice how much smaller this is, right, than the rotational inertia of a hoop. Okay, if we had a hoop that was around here, right, it would have a different, much bigger rotational inertia. And that's because the mass is not all on the outside. It's, along the inside here too. Right? The mass is all different distances away from the axis. Now, again, you should memorize this. You should just know this. If it's a thin rod rotating about an axis through its center, it's 1/12 ml squared. When we're done deriving all these, I'll give you a single sheet that has all of the basic formulas on it. You'd find one on the internet, but I'll give you one. They are not on the equation sheet, though. Right? But the thing is here, you're supposed to be able to prove these. So you have to be able to do this integral. You have to be able to do the change of variable, right, we did here. Without the change of variable, you can't do this integral. So you have to be able to employ the linear density and know what it is. Okay, so if you want those 3 points on a test, right, you got to learn that stuff. Okay, next one. A solid disk of mass m and radius r and uniform density, okay, about an axis through its center. So the axis is, that's the radius is r, right? And there's the axis of rotation. Can you see the three-dimensional aspect here, right? So this would spin, or again, if it was rolling, okay? So the total disk has a mass m and a radius r. Now, this is tougher. Why? Because the rod was one-dimensional. This is obviously two-dimensional. That's going to make our change of variable more complex, as you will see momentarily. So again, what we want to do here is to break this up into infinitely small little pieces of mass and sum all the rotational inertias of all those little pieces. right? But what we're going to do here is to break this thing up. Instead of into little pieces, we're going to break it up into little hoops. Okay, these hoops will have mass dm. Okay, they have a radius little r, inner radius little r, and a thickness dr. Now, because we're using dr and dm, my drawing is a huge exaggeration, right? These would be infinitesimally thin to be able to do an integral. Okay, to be able to capture all of this. Because if we cut them into these big, this is actually called an annular cylinder when it's got a hole in the middle and a thickness to it. But when you cut them up into those pieces, right, there might be overlap or underlap here when we're done, right? Little pieces that aren't exactly the same size. So we have to break them down again, do the integral by shrinking their width, their dr, to make them infinitesimals. So don't get confused by my drawing. I drew it thick so that we could see it, right? But when we do the calculus, we're talking about infinitesimals. So this is the integral of r squared dm. But the density of the disk is constant. So we can do a change of variable, but we're not going to use three-dimensional density, and we're not going to use linear one-dimensional density. We're going to use two-dimensional density, which does not, for some reason, have a special name or a special symbol. So the overall density of the entire disk would be mass per unit area. Capital A is area. Right? The density of the little piece here would be dm over dA. Right? The mass of this little piece over the area of that little piece. You with me? And these are the same because it's uniform or constant density. Right? It's a uniform density disk. Okay, so the reason I don't write it out like the other one is because there isn't a special, I don't know why, but there isn't a special symbol for two-dimensional density. Okay, so this is the overall density. This is the density of the little piece, but since it's uniform, they have to be the same. Now, the question becomes, how do we write out dA? Well, dA is going to be the area of this, right? So how are we going to figure out what the area of that is? Well, if you look at the outside edge, right, isn't that a circle? And we know the area that would be inside that circle. We did that, lab, right? It's pi r squared, the radius of this outside. So if we take the area of the outside circle and we subtract off the area of the inside circle, what we get the area in between? Let me say that again. The area of the outside circle minus the area of the inside circle will give us the area in between. Each one of those is pi r squared. So now we have to be careful with how we've defined everything. The radius of the outside circle is little r plus dr. Right? So this is the area of the outside circle. It's pi, the quantity r plus dr squared. And the inside circle has an area of pi little r squared. Okay with that? Geometry. Square. And notice that if we were to distribute through, this pi r squared minus that pi r squared would cancel. Then here's a little tricky calculus thing. dr is essentially an infinitesimal, right? If we square something that's vanishingly small, what do we get? We get something that's even more vanishingly small. So essentially, this is 0. I know that's a weird thing, depending on how much calc you have, but this is the calculus of infinitesimals, derivatives and integrals. Okay? So dr squared is essentially 0, which leaves us with an area of 2 pi r dr. Now take a look at that, and you might be able to convince yourself that this is okay without having done this. I used to try to prove it that way to students, but this seemed to help to see this written out. So 2 pi r is the circumference of this inner one, right? And then if you multiply by the thickness, that's dr, you get the area of it, yeah? It works because we're using infinitesimals. So we plug that in right there. We solve for dm, because we want to do a change of variable. And we get dm equals m over a times 2 pi r dr. We plug that in, and we will change our variable. Now, we also have to talk about limits of integration. Well, what will the radius of the smallest possible piece we could pick be? 0. And what would the radius of a piece on the outside be? Capital R. So our limits of integration will go from 0 to capital R. That will pick up all of these, right, from the inside all the way out to the outside. And note here, we've got r squared times our little change of variable thing. Now, 2, pi, the total mass, the total area are all constants, so they can get pulled outside the integral. And this fairly complex looking integral simplifies. Note that we've got an r squared times an r, which is r cubed. See that? That r and that r squared become r cubed. And the integral of r cubed with respect to r, add 1 to the exponent, divide by the new exponent. So it's 1/4 r to the 4th. And now we just need to evaluate it at capital R minus evaluating it at 0. Well, of course, when we evaluate this at 0 and we plug a 0 in here, 0 times 1/4 is 0, and 0 times all that is 0. So when we evaluate it at 0, we get 0. When we evaluate it at R, we get this. Okay? Now, problem is, we've still got this area thing. But we know that the area of the entire disk is going to simply be pi r squared. Note how we're dealing with this as a two-dimensional object. We're not worrying about the thickness of it. Just as we didn't worry about the thickness of the rod, we considered it a one-dimensional object. Okay? And you'll see why in a moment. So this is pi r squared. We plug that in for the area. The pi's cancel. 2 of the r's cancel. And we get 1/2 mr squared. A thin, solid disk about a central axis. This one gets used quite a bit because they roll really well. Right? So it's 1/2 mr squared. And hopefully that kind of makes sense. Right? As it's the rotational inertia kind of halfway, right? Because there's mass on the inside and there's mass on the outside, and so they just kind of all cancel out to the middle. Yeah? Like if you were going to predict what it might be, you might come up with 1/2. You okay with that? That one's hard, all right? I don't know if I've ever seen them actually ask for you to do that entire integral. Although on occasion what they might do is ask you to do something like write out the integral you would need to be able to solve this. So they may expect you to be able to get to something like this with the limits of integration and the change of variable, right? And then they say, okay, if you can do that, you can do the calculus. Again, 2 or 3 points. If you have to skip it, they'd probably tell you, or you would just know that the rotational inertia of a thin rod about a central axis is 1/2 mr squared. Woohoo, that one was a big one. So like we did with the hoop, we went from a hoop to a cylindrical shell. So now let's go from a solid disk to a solid cylinder. I know this looks like my cylindrical shell, but this one's full up completely. Hard to see in the picture, but it's full up completely, okay? It's a solid cylinder. About a central axis, so again, the axis goes through there. Okay, so this is a full up can, if you will. All right, a solid cylinder. Well, what we're going to do here is much like we did with a cylindrical shell. Rather than redo the calculus, we're going to break up this solid cylinder of radius r into a bunch of disks. Each disk has a mass mi. And then we are going to sum the rotational inertia of each one of those disks, right, as we go from the bottom to the top, and that will capture the total rotational inertia. As we just proved, the rotational inertia of each disk is 1/2 mi r squared, where mi is the mass of each little disk. But 1/2 and r are constants in this case, because it's a cylinder. Right? So all the disks we would cut out would have the same radius. Perpendicular distance from the axis of rotation again, right? So if we factor that out, we get 1/2 r squared sum of all of the mi's, and the sum of all the mi's is the total mass. So just like a hoop has the same rotational inertia as a cylindrical shell of the same mass and radius, a disk has the same rotational inertia as a solid cylinder of the same mass and radius. And that, got to be careful there. They got to have the same mass and radius. Okay, so you can't compare this disk to the entire solid cylinder. You'd have to compare a disk that has this radius but somehow has the same mass as the whole cylinder to get the exact same rotational inertia. Otherwise, you'd be plugging in different numbers here. Okay, so you got to be a little careful here. I know the symbols are a little weird. That is why back in the last proof, I didn't worry about the fact that my disk had a little thickness to it. It really doesn't matter. Okay, it comes out of the calculus. Whew, that is a lot of proofs. So, next up is going to be, well, if you notice, all the ones we did were through the center of mass, right? Whether that was the thin rod, the solid disc, even the hoop that we did, and the cylindrical shell, and the disc, and the solid cylinder, right? We're all through mass, through axes that went through the axis of rotation. What if they don't go through the axis? What if the rotation is not through the center of mass? Right? What if somehow we like attach an axis out here to this edge and let it rotate around that axis? What would the rotational inertia be? Well, we could redo the calculus, right? But then every time we had a different axis, we would have to redo the calculus to find the rotational inertia. There is a way to come up with an easier way to convert the rotational inertia about the center of mass to the rotational inertia about any other axis in here. If you know the way to do it, this is our next lab, all right, that we're going to begin. So this is the next movie to watch. Will tell us kind of how we're going to set up the lab to figure out that math model.